It is a pervasive assumption in modern psychology. Incompetent people lack the metacognitive capacity to realize they are incompetent. Their lack of skill creates a dual burden, ensuring they make errors and robbing them of the ability to recognize those very errors. The idea has deep historical roots. Charles Darwin observed over a century ago that ignorance more frequently begets confidence than does knowledge. In 1999, psychologists Justin Kruger and David Dunning published a seminal paper formalizing this observation into a scientific axiom. The methodology of their study was straightforward. The researchers asked subjects to complete a test measuring logical reasoning, grammar, or humor. Immediately afterward, participants were asked to estimate their own performance percentile. This chart from the study shows the findings that made the paper famous. While top performers slightly underestimated their skills, individuals in the bottom quartile drastically overestimated their abilities. Scoring in the 12th percentile, they routinely estimated their performance to be above the 60th. This specific visual convinced multiple academic disciplines that human beings possess an inherent metacognitive blind spot. For decades, the Dunning-Kruger Effect stood as an unchallenged law of behavioral science. Yet, the entire premise relies on a rudimentary mathematical error. The classical Dunning-Kruger Effect is entirely invalid. To understand the flaw, we have to look at the math behind the original 1999 study. First, we define a participant's actual test score as the variable x. Next, we define the participant's perceived score, their self-assessment, as the variable y. To calculate the degree of miscalibration, or the self-assessment error, the researchers subtracted the actual score from the perceived score, y minus x. The researchers plotted this error, y minus x, directly against the actual test score, x. In statistics, this is known as autocorrelation. By plotting y minus x against x, you are correlating a variable with the negative version of itself. Because x appears on both sides of the comparison, the mathematical design guarantees a downward-sloping correlation. It will produce this curve regardless of any underlying human psychology. We can prove this by removing human behavior entirely. If we generate a dataset of purely random numbers, statistical noise containing zero psychological data, and process it through Dunning and Kruger's formula, the result is identical. This scatterplot shows how random noise, when subjected to autocorrelation, perfectly replicates the exact curve published in the 1999 paper. This chart shows what happens when the math is corrected. In 2017, researcher Edward Neufer retested the theory using statistically independent variables, completely eliminating autocorrelation. The resulting trend line is entirely flat. There is no systemic assessment bias. The classical Dunning-Kruger effect is a statistical myth. However, the mass integration of artificial intelligence into clinical and expert workflows is now engineering this exact cognitive deficit into reality. In the modern clinical workflow, specialists increasingly interact with frictionless, highly fluent AI interfaces that generate plausible diagnostic and treatment recommendations in seconds. As clinicians interact with these systems, a shift occurs in their self-perception. They begin to attribute the high-quality, high-speed output of the algorithm to their own innate cognitive competence. This creates a replication illusion. When the AI produces a successful outcome, the user convinces themselves they have mastered the domain, ignoring the fact that the software acted as a cognitive exoskeleton. In recent experiments, participants using AI saw a modest actual improvement of 3 points, but perceived performance spiked by 4 points. The AI destroys traditional competency distributions. It flattens the curve, pushing all users toward a high-confidence, high overestimation state. Counterintuitively, higher literacy with AI tools correlates with less accurate self-assessment. The more comfortable the user is with the system, the more aggressively they offload their mental processing. In clinical psychology and radiology, this causes severe cognitive atrophy. Highly trained diagnosticians degrade into passive editors of machine-generated reports, heavily susceptible to automation bias and vigilance decrement. AI integration suppresses the reflective reasoning required to identify errors. It generates an epistemic distortion field, where perceived competence and actual performance diverge. The standard industry response to black box over-reliance is the implementation of explainable AI, paired with strict mandates to keep a human in the loop. The logic assumes that if the system provides a detailed description of its reasoning, the human clinician is empowered to verify the logic and catch algorithmic errors. To test this transparency hypothesis, researchers conducted a lab-in-the-field experiment with 257 medical students, making thousands of diagnostic decisions. This probability diagram shows the exact impact of explainable AI. When the algorithm is correct, providing an explanation increases diagnostic accuracy by 4.3 percentage points. But when the algorithm is incorrect, the presence of an explanation decreases accuracy by 4.6 percentage points. The persuasive structure of the explanation acts as a cognitive anchor. The machine's narrative justifies its conclusions so cleanly that it becomes highly difficult for the clinician to override the false output. These algorithmic hallucinations do not sound like glitches. They perfectly mimic causal medical reasoning and are delivered with high confidence scores. Bayesian analysis of this data exposes the severe danger in how users calculate machine accuracy. Decision makers treat explained AI as having a 15.2 percentage point higher accuracy rate than its objective mathematical capability. This reveals a transparency paradox. Universal explanations may systematically bind human decision makers to incorrect logic, creating a specific, measurable risk of over-reliance. This overconfidence is not restricted to individual clinicians. It routinely infects the developers building these tools, who mistakenly assume that predictive performance in a lab guarantees generalizability in the field. The premier case study in institutional overestimation is the EPIC sepsis model. During internal testing, the system produced pristine laboratory metrics. It achieved an area under the curve score of 0.95, indicating near-perfect predictive accuracy. External validation exposed a specific failure in the model's logic. It had failed to learn the physiological signs of sepsis, learning instead the spurious correlations unique to the training hospital. This diagram shows the disconnect. While developers intended the AI to track vital signs, the algorithm was actually tracking administrative shortcuts, mapping the specific timing of lab orders and documentation practices. When deployed to over 100 hospitals, the model triggered a massive surge in false alarms. The algorithm's inability to adapt to new clinical contexts devastated workflows and induced profound alert fatigue. Operating at superhuman speeds with opaque logic, systems like this create out-of-the-loop unfamiliarity. They turn human clinicians into liability sponges, positioned to take the blame for systemic failures they cannot reasonably prevent. Optimizing an algorithm purely for statistical laboratory metrics without designing for contextual awareness reliably produces technical excellence followed closely by catastrophic clinical failure. Preventing these failures requires an engineering pivot. Pure predictive optimization must be replaced by system architectures explicitly grounded in epistemic humility. One proposed solution is the Bodhi framework, a dual reflective system architecture designed to maintain mutual accountability between the algorithm and the clinician. This diagram shows the system structure. It begins with a curiosity module. This node constantly scans incoming data, explicitly looking for variables that fall outside the model's original training distribution. Instead of forcing an answer, the curiosity module searches for anomalies the core model might confidently misinterpret. When an anomaly is detected, the humility module triggers. It quantifies uncertainty and escalates the highly ambiguous case directly to a senior clinician. To function, these architectural concepts must translate directly to the user interface through cognitive forcing tools, deliberate interventions that disrupt automatic thinking. For example, an interface might implement an explain back requirement. If a physician attempts to override or accept a highly uncertain AI flag, the system physically halts the workflow, requiring the human to type a specific clinical rationale before they can proceed. Medical AI requires a shift toward calibrated partnerships, where technological innovation and human wisdom function in a humble, life-saving alignment.